Throughout history, one of the deepest and most unsettling questions humanity has ever asked is this: how could nothing exist before the Big Bang? This question feels almost paradoxical because we are wired to think of things in terms of beginnings and endings, of causes and effects. Yet, when we try to trace the universe back to its absolute beginning, we hit a wall. The idea that before everything there was nothing seems both incomprehensible and unsettling. Was there truly nothing, or was nothing itself something different than what we imagine? This mystery sits at the crossroads of physics, philosophy, and human imagination, and it challenges not just our science, but the very way we understand existence itself. When we wrestle with the mystery of nothing before the Big Bang, the conversation naturally leads us to understand what the Big Bang itself actually means. Many people hear the term and imagine an explosion, a gigantic cosmic firework bursting into empty space. But that mental picture is misleading. The Big Bang wasn't an explosion in space. It was the expansion of space itself. It wasn't that the universe expanded into something. It was that the fabric of reality, space and time, unfolded from a hot, dense, unimaginably tiny state. In fact, when scientists use the phrase Big Bang, they're referring not to a single bang-like event, but to a rapid expansion that set the stage for everything that would follow. The birth of matter, energy, galaxies, stars, planets, and eventually, us. To appreciate what the Big Bang Theory explains, we need to retrace cosmic history as far back as modern science allows. About 13.8 billion years ago, according to the best evidence from cosmology, the universe was compressed into a state of extraordinary density and temperature. Every particle, every photon, every possibility of existence we now observe was bound together in a single compact state. And then, for reasons we still don't fully understand, this state began to expand. In the first tiny fraction of a second, so brief that our minds can barely grasp the scale, the universe went through dramatic changes that shaped its future. Matter and antimatter were created, forces began to differentiate, and a cascade of physical laws unfolded. What makes the Big Bang Theory so powerful is not just that it provides a story for the universe's beginning, but that it is supported by compelling evidence. First, there's the observed expansion of galaxies. In the 1920s, Edwin Hubble discovered that galaxies are moving away from us, with more distant galaxies receding faster. This is exactly what we would expect if space itself is stretching, a direct echo of that primordial expansion. Second, there's the cosmic microwave background radiation, a faint afterglow permeating the universe, discovered accidentally in 1965. This radiation is the cooled remnant of the early hot universe, like heat left over from a fire long since burned. It's one of the most striking confirmations of the Big Bang model. Third, there are the abundances of light elements, such as hydrogen, helium, and lithium in the universe. Their observed ratios match beautifully with predictions made by Big Bang nucleosynthesis, the process by which the first atomic nuclei were forged in those early minutes. Yet, while the Big Bang explains the observable unfolding of the cosmos, it does not tell us what happened at the beginning, nor does it fully explain what, if anything, came before. The theory is incredibly effective at describing the evolution of the universe from a fraction of a second onward. But as we push closer to that initial singularity, physics, as we know it, begins to break down. The equations of general relativity, which describe the curvature of spacetime, work wonderfully until they reach that infinitely dense point. At that boundary, the laws no longer produce sensible predictions. This is why cosmologists say that the Big Bang Theory describes the universe's expansion from its earliest observable moments, but not the very instant of creation. And here lies the subtle but crucial point. When we ask what happened before the Big Bang, we may be asking a question that the Big Bang framework itself cannot answer. The concept of before presumes that time existed prior to the universe's unfolding. But if time itself began with the Big Bang, then the word before might be meaningless, like asking what's north of the North Pole. This is why so many scientists and philosophers find this question endlessly fascinating, because it forces us to reconsider the limits of our concepts of time, space, and nothingness. Interestingly, the Big Bang is not the only way scientists describe the universe's origin, but it is the most widely supported by observation. Alternative theories such as steady-state cosmology once tried to argue that the universe had no beginning, that new matter was continuously being created as the cosmos expanded. But the discovery of the cosmic microwave background was essentially the final blow to that idea. The evidence overwhelmingly supports the notion that the universe had a hot, dense origin. That said, hot and dense doesn't necessarily mean from nothing. This distinction is where the real mystery lies. So, when we define the Big Bang, we're talking about the rapid expansion of the universe from a compressed state of energy and matter about 13.8 billion years ago, supported by overwhelming observational evidence. But it leaves us with a lingering question. Did this event mark the absolute beginning of everything? Or was it merely the beginning of the universe as we know it? Was it the first page in the cosmic book, or just the start of a particular chapter in a much longer, perhaps infinite narrative? This tension between what science can explain and what remains elusive is exactly why the Big Bang is both a cornerstone of modern cosmology and a doorway to deeper mysteries. When we begin to explore the concept of nothing, especially in the context of what may have existed before the Big Bang, we quickly discover that this word is more slippery than it appears at first glance. In ordinary language, nothing means emptiness, the total absence of everything. If you clean out a box, you might say there's nothing inside it. If a room is vacant, we call it empty. But in both cases, the nothing is still something. It is space, a container, a location where other things could exist. When scientists talk about nothing in the cosmological sense, they are often referring to the absence of matter, energy, space, and even time itself. That is a much deeper kind of void, and yet, as strange as it sounds, even that absolute absence may not truly be nothing in the strictest sense. For centuries, philosophers and scientists debated whether a true void could exist. Aristotle, for example, denied the possibility of a vacuum, believing that nature abhors emptiness. Centuries later, as science advanced, the idea of empty space became more acceptable, and physics began to treat a vacuum as a genuine state of nothingness. But modern physics has revealed that even in the emptiest vacuum imaginable, there are still rules, structures, and hidden layers of activity. So the problem is this. Every time we peel away one layer of what we think is nothing, we discover that it has properties, behaviors, and consequences. This becomes clear when we examine the notion of nothing as the absence of space and time. According to relativity, space and time are inseparable aspects of reality, woven into a four-dimensional fabric called space-time. If we imagine stripping them away, we're left with not just an empty box, but with the absence of the very arena in which existence could unfold. That seems like the ultimate definition of nothing. Yet, theories in quantum physics complicate this picture. Some suggest that even if space-time were removed, there may still be underlying laws, potentials, or mathematical frameworks that exist in some form. In this sense, nothing might be a fertile ground from which universes could emerge, a kind of hidden scaffolding rather than a blank void. Consider the way quantum mechanics reframes emptiness. In quantum theory, a vacuum isn't a passive void, but a restless, fluctuating field. Even in the absence of particles, energy can momentarily appear, and virtual particles can flicker in and out of existence. If that's true, then nothing at the quantum level is not truly nothing. It's a boiling cauldron of possibilities, an invisible stage where potential realities are constantly bubbling into and out of existence. This realization undermines the classical notion of emptiness and suggests that the seed of something may be inherently built into what we call nothing. This redefinition of nothing has profound implications when we return to the question of the Big Bang. If what we think of as nothing already carries within it the possibility of fluctuation, then the birth of the universe may not require an external cause in the way we usually imagine. Instead of a miraculous leap from true void to cosmic abundance, it could be that nothing always had within it the latent ability to become something. To us, this may sound paradoxical, but within the framework of physics, it is a way of reconciling the apparent contradiction of existence springing from non-existence. There's another fascinating layer to this. Some physicists argue that even the laws of physics themselves might not require a pre-existing universe to exist. They may instead be fundamental truths, timeless and abstract, waiting to manifest in a physical reality. In this view, nothing could still be governed by mathematical structures that act as a hidden order beneath the void. That means that when we ask whether there was nothing before the Big Bang, we may actually be asking the wrong question, because the very idea of nothing could be an illusion. And so, we find ourselves standing in front of a strange paradox. To us, nothing feels like the absence of everything. But the more carefully science examines it, the more it seems like nothing has properties, rules, and potentials. What we might call nothing could in fact be a disguised something, just not a something that we easily recognize. This is why so many scientists and philosophers caution against taking the word nothing at face value in cosmology. It may be the most misleading word in the entire discussion. When we attempt to trace the universe back to its very beginning, we eventually collide with the harsh boundary known as the limits of physics. Our two most successful frameworks for describing the cosmos, Einstein's general relativity and quantum mechanics, work brilliantly in their own domains. General relativity describes the large-scale structure of spacetime, gravity, and the expansion of the universe. Quantum mechanics explains the microscopic world of particles, forces, and uncertainty. But when we push both to their extremes, when we try to apply them to the singularity at the start of the Big Bang, they no longer fit together. The equations begin to break down, producing infinities and nonsensical answers, as if the universe itself is saying, "You cannot look beyond this point with the tools you currently possess." The singularity is the core of the problem. According to classical general relativity, if you follow the expansion of the universe backward in time, everything converges into an infinitely dense, infinitely hot point, a singularity. But infinities in physics are almost always signs of incomplete understanding, not actual features of reality. For example, when earlier physicists calculated the energy of an electron orbiting an atom using classical mechanics, they ran into infinities. It was only when quantum theory emerged that those infinities were resolved and replaced with meaningful predictions. In the same way, the singularity at the Big Bang is not likely a real thing, but a signal that our current theories are inadequate at such extremes. This is why asking what came before the Big Bang is so problematic. The word before assumes that time existed in some meaningful way prior to the expansion. But if general relativity is correct, time itself is a feature of spacetime, and spacetime began with the Big Bang. In other words, the Big Bang wasn't just the beginning of matter and energy, it was the beginning of time. From this perspective, the question what came before may be meaningless, like asking what lies south of the South Pole. It isn't that there's some hidden land we haven't yet discovered, it's that the question itself doesn't apply. Our physics runs out of language, runs out of framework, and the question of before dissolves into paradox. Yet this limitation also sparks creativity. Physicists have not been content to simply accept the breakdown of theory at the singularity. They have been striving for decades to create a deeper, unified theory that combines relativity and quantum mechanics, a theory of quantum gravity. Candidates like string theory, loop quantum gravity, and other approaches attempt to reconcile the smooth curvature of spacetime with the jittery fluctuations of quantum fields. While none have been definitively proven, these theories suggest that the singularity might not be a true beginning, but rather a doorway into new physics. Instead of an infinite density, the early universe could have been governed by exotic rules where space and time were quantized, behaving in discrete chunks rather than continuous flows. One striking idea that emerges from these attempts is that the universe may have had a finite but non-singular origin. For example, in loop quantum cosmology, the equations suggest that the universe could have undergone a bounce. Rather than collapsing into an infinitely small point, a prior universe could have contracted to a very dense but finite state, and then bounced into expansion, the Big Bang. In this case, our universe may not have been the first act, but part of an eternal cycle of contraction and expansion. The singularity disappears, replaced by a transition governed by quantum laws. Another way physicists approach the limits of our theories is by rethinking what time actually means. If time is emergent rather than fundamental, if it arises from deeper structures like entanglement or information flow, then the Big Bang might not represent a hard beginning. Instead, it might mark the boundary where our familiar concept of time crystallized out of a more fundamental, timeless state. This is an idea many physicists and philosophers explore, that asking before the Big Bang is not about chronology at all, but about the conditions that gave rise to the very possibility of chronological experience. It's important to emphasize that when we say our theories break down at the singularity, it doesn't mean physics becomes useless. It means that the mathematics we rely on to describe the universe gives us nonsense, like dividing by zero. This tells us the theory is incomplete, but it also points us toward where new discoveries may lie. For instance, black holes present a similar problem. General relativity predicts singularities at their centers as well. Studying black holes and their horizons may ultimately help reveal the kind of physics that can explain the Big Bang. The event horizon of a black hole hides what's inside from us, much as the horizon of the Big Bang hides the before from our current understanding. Both situations suggest that nature is keeping its secrets behind walls of mathematics we cannot yet penetrate. Even with these limits, cosmologists have been able to learn extraordinary things about the early universe. Using satellites like COBE, WMAP, and Planck, we've mapped the cosmic microwave background radiation in exquisite detail, giving us a snapshot of the universe when it was just 380,000 years old. These measurements reveal subtle ripples that seeded galaxies, clusters, and cosmic structures. But try to peer further back, closer to the singularity, and our theories blur. It's as though we have a clear photograph of a child, but a foggy, distorted sketch of the newborn. The singularity remains shrouded in mathematical mist. When we arrive at the question of time itself in the context of the Big Bang, we begin to wrestle with something far more profound than just clocks and calendars. Time is so deeply ingrained in our human experience that it feels like the most obvious, unquestionable feature of reality. We measure our lives by it. Every cause and effect we've ever known is defined by it. But the moment we ask, what happened before the Big Bang? We are forced to confront the possibility that time may not be fundamental at all. It may not extend endlessly in both directions like a straight line. Instead, time itself may have started at the Big Bang, which means the very word before could be meaningless in a cosmological sense. Einstein's theory of general relativity gave us a dramatic shift in how we think about time. Rather than being a separate, independent flow that ticks uniformly everywhere in the cosmos, time is intimately bound to space in what we now call space-time. Massive objects warp this fabric, and the flow of time changes depending on where you are and how you move. A clock near a black hole ticks slower than one on Earth. A particle moving close to the speed of light experiences time differently than a stationary observer. What this tells us is that time is not absolute. It's flexible, dynamic, and interwoven with the universe's structure. So when we apply this understanding to the Big Bang, we realize that if space itself had a beginning, time did too. This is a concept many people find deeply unsettling because our language and logic assume a temporal framework. We can't help but ask, but what was there before time began? What caused it to start? These questions reflect our intuition, shaped by everyday cause and effect reasoning, but they may not apply to the ultimate structure of reality. If time began at the Big Bang, then asking what came before is like asking what lies north of the North Pole. The question uses a word that doesn't fit the context. It's not wrong because we lack information. It's wrong because it doesn't make sense within the framework of space-time itself. This doesn't mean the question is meaningless in the broader sense. It pushes us to reconsider time not as a fundamental backdrop of existence, but as a property that emerges under certain conditions. Some physicists propose that time could be emergent, like temperature. Temperature doesn't exist at the level of individual atoms. It's a collective property of many particles moving together. Similarly, time might not exist at the most fundamental level of reality. Instead, it could emerge when systems of particles interact, when entropy increases, or when space-time itself comes into being. The Big Bang, in this light, may represent the phase transition where timelessness gave way to time as we experience it. There's also the question of whether time might be cyclical or multidimensional. In some models of the universe, time doesn't stretch infinitely back, but loops. In such models, the Big Bang could be less of a beginning and more of a moment in a repeating cycle, a renewal of cosmic evolution. This idea challenges our instinct to think of time as a single arrow pointing forward from the past into the future. Instead, time could be a closed curve, a loop that eventually folds back into itself. Philosophically, this reshapes the conversation about causality. Normally, we think that every effect must have a cause and that every cause must precede its effect in time. But if time itself had a beginning, then the Big Bang may not need a cause in the sense we understand it. There may not have been a moment before for a cause to operate within. In this view, the universe doesn't require something external to spark it into being. The Big Bang may be a boundary condition, the point where time itself begins. Stephen Hawking once compared it to asking what lies south of the South Pole. The question itself doesn't apply because the concept of south ceases to make sense beyond that point. Similarly, the concept of before may simply not apply to the origin of time. Yet, this doesn't mean that physicists and philosophers stop asking. Instead, they broaden the scope of what time might mean. Some approaches in quantum cosmology, for example, describe the early universe without using time at all. Instead, they describe it in terms of timeless states that evolve into our experience of time as the universe expands and structures form. In this framework, what we perceive as a flowing timeline may simply be a way that conscious observers organize information, not an intrinsic feature of the universe itself. This perspective also raises profound questions about our perception of existence. If time began at the Big Bang, then our desire to know what came before may be a product of human imagination rather than cosmic necessity. Our brains evolved to think in terms of causes, sequences, and narratives. That's why myths of creation almost always describe some event that happened before. But modern physics challenges this instinct, suggesting that the universe may not conform to our need for a tidy sequence of events. The Big Bang could have been the point at which the story itself began, not just the first chapter, but the very invention of the concept of chapters. So when we think about time in relation to the Big Bang, we are forced to stretch our imagination beyond linear thinking. Time may not be an infinite line extending into the past. It may be a loop, a bubble, or an emergent property that appeared along with the universe itself. The Big Bang may not represent a cause that demands something earlier, but instead the horizon beyond which the concept of earlier simply dissolves. In grappling with this, we find ourselves at the edge of human understanding, where science, philosophy, and imagination blur together. And perhaps this is the most humbling realization of all, that time itself, the thing we most take for granted, may be the greatest illusion in the entire cosmic story. If time itself may have begun at the Big Bang, then our next step is to understand the framework that allows us to even talk about time, space, and their expansion. Einstein's general relativity. This theory, first published in 1915, was one of the most revolutionary achievements in human thought. It replaced the Newtonian view of gravity as a simple force with the idea that gravity is the warping of space and time caused by mass and energy. Instead of thinking about planets being pulled by invisible forces, general relativity describes them as objects moving through curved space-time. That shift changed everything about how we think of the cosmos. When applied to the universe as a whole, general relativity gave us a profound new picture. The equations didn't describe a static universe, as many scientists at the time assumed, but one that was either expanding or contracting. Einstein himself was so convinced that the universe had to be eternal and unchanging that he added a cosmological constant to his equations to force a static solution. Later, when Hubble discovered that galaxies were receding from us, Einstein realized his modification was unnecessary and famously called it his greatest blunder. In fact, general relativity naturally predicts an evolving cosmos, one that stretches and changes over time. This framework allows us to describe the expansion of the universe as space itself growing larger. The galaxies aren't flying through empty void like shrapnel from an explosion. They're carried along by the stretching of space-time itself. Imagine dots on the surface of a balloon. As the balloon inflates, the dots move away from each other, not because they're moving across the balloon, but because the surface itself is expanding. Similarly, galaxies move apart not because they're speeding through space, but because the fabric of space-time is expanding beneath them. This elegant description, however, comes with a catch. General relativity is a classical theory. It works beautifully on large scales: stars, galaxies, black holes, the evolution of the cosmos. But as we approach the beginning of the universe, the conditions become extreme. Densities and energies skyrocket, Quantum effects dominate, and general relativity alone can't capture what's happening. At the singularity, the equations blow up, spitting out infinities that don't correspond to physical reality. The theory describes the expansion of space-time after the Big Bang, but it doesn't tell us what, if anything, happened before that expansion began. It draws the boundary of our knowledge but cannot cross it. This is where the tension between relativity and quantum mechanics becomes unavoidable. General relativity treats space and time as smooth, continuous, geometric fields. Quantum mechanics, on the other hand, deals with probabilities, discreteness, and uncertainty at the smallest scales. As long as we keep these domains separate, relativity for the large, quantum theory for the small, they both work. But at the Big Bang, where the entire universe was both extremely small and unimaginably dense, both sets of rules should apply simultaneously. And yet, they refuse to coexist peacefully. The clash between them shows us exactly where new physics is needed. Some attempts to reconcile the two suggest fascinating possibilities. For instance, string theory proposes that spacetime itself may not be fundamental, but instead emerges from the vibrations of tiny strings in higher dimensions. Loop quantum gravity proposes that spacetime is granular, woven from tiny loops rather than smooth and continuous. In these approaches, the singularity may not be a real boundary at all. Instead, general relativity's failure near the Big Bang signals that the true nature of spacetime is something deeper, and perhaps the universe never reached an infinite density at all. But until such theories are confirmed, general relativity remains silent about what came before. It simply tells us, here lies the horizon of knowledge. Within its framework, space-time starts with the Big Bang, expands, evolves, and shapes the universe we observe. Beyond that origin point, relativity cannot speak, and that silence is both frustrating and tantalizing. It leaves the door open to speculation, to deeper theories, to the possibility that the story of the cosmos is stranger than even Einstein could have imagined. What's remarkable is that even with these limits, general relativity continues to be one of the most accurate theories we have ever devised. Its predictions have been tested again and again, from the bending of light by gravity to the recent detection of gravitational waves. It describes black holes, expanding space, and the curvature of the cosmos with breathtaking precision. And yet, as brilliant as it is, it also humbles us. It reminds us that no single theory may ever tell the full story of the universe. Einstein gave us the grammar of spacetime, but not the opening sentence of the cosmic book. And this is why the role of general relativity in the Big Bang story is both foundational and limited. It explains how the universe expands, how time flows, how matter curves the very stage it inhabits. But it does not tell us what set the stage itself. It shows us the play unfolding with incredible clarity, but keeps the prologue hidden behind a curtain we cannot yet lift. In that silence lies one of the greatest mysteries of all. Not just how space and time behave, but how space and time themselves came to be. General relativity gave us a breathtaking picture of an expanding universe, but as we saw, it falters at the singularity. To venture further, we need to look at the other great pillar of modern physics, quantum mechanics. Where relativity rules the vast, quantum theory governs the minute, and its lessons about nothingness are nothing short of astonishing. If Einstein taught us that time and space are dynamic, quantum physics teaches us that emptiness itself is an illusion. What we call nothing in the quantum world is never truly empty. It seethes with fluctuations, uncertainty, and hidden potential. At the heart of quantum mechanics lies the principle of uncertainty, formalized by Werner Heisenberg in the 1920s. Unlike in classical physics, where objects have definite positions and velocities that we can measure in principle with unlimited precision, quantum systems resist such certainty. The more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This is not a limitation of our instruments, it is a fundamental feature of reality. The quantum world is probabilistic at its core, not deterministic. What exists isn't a fixed trajectory, but a cloud of possibilities, described by wave functions that collapse into definite outcomes only when observed. Now, apply this uncertainty to the vacuum of space. Classically, we might imagine a vacuum as complete emptiness, a silent, inert nothingness. But in quantum field theory, the vacuum is alive with activity. Because of uncertainty, energy cannot be pinned down to absolute zero. Even in the absence of particles, fields fluctuate, bubbling with fleeting amounts of energy that manifest as pairs of virtual particles. These ghost-like particles appear and disappear so quickly that they evade direct detection, but their presence has measurable effects. They cause shifts in atomic energy levels, create forces between uncharged plates, the Casimir effect, and even influence the large-scale structure of the cosmos. This means that nothing, as seen through the lens of quantum mechanics, is far from empty. Instead, it's a restless foam, a background buzzing with ephemeral possibilities. These quantum fluctuations are not rare accidents. They are built into the very fabric of existence. In fact, the more closely we peer into what we think is emptiness, the more we find activity. It is as though reality cannot help but generate temporary sparks of being, even when stripped of everything we would call something. And here's where this fight reshapes our discussion of the Big Bang. If nothing is unstable, if it is always writhing with potential fluctuations, then the leap from nothing to something may not be as impossible as it first sounds. A fluctuation in the quantum vacuum could, in principle, give rise to a universe. The seeds of existence may not have required an external push, but instead could have sprung from the inherent instability of nothingness. This doesn't mean universes are popping into existence around us all the time in ways we could see, but it suggests that the very laws of quantum physics make the birth of universes conceivable. It is worth pausing here to recognize how radically this challenges our intuition. In daily life, nothing is nothing. An empty glass has no water. An empty room has no people. But the quantum world plays by different rules. Its nothing is not the absence of reality, but a state rich with potential. A stage on which particles dance in and out of existence, unseen, yet consequential. Even the vacuum has energy, a property known as vacuum energy, that may hold the key to cosmic mysteries like dark energy and the accelerating expansion of the universe. What quantum uncertainty reveals, then, is that we must abandon the classical idea of perfect emptiness. There is no such thing as a perfectly calm void. Instead, there is only fluctuation, instability, and the ceaseless potential for creation. For cosmologists, this insight is electrifying because it bridges the gap between nothing and something. The Big Bang may not have required a miracle or an outside cause, but may have been a natural expression of the uncertainty built into reality itself. But this insight also deepens the mystery. If even nothing seethes with activity, we are left to ask, why does the quantum vacuum exist in the first place? Why do the laws of physics allow for fluctuations instead of a true, featureless void? Perhaps the question of why there is something rather than nothing remains, but quantum mechanics shows us that nothing is never truly nothing, and maybe never could be. Building on the strange revelations of quantum uncertainty, we come face to face with one of the most fascinating and counterintuitive ideas in modern physics, the concept of vacuum energy. At first glance, it sounds contradictory. How can a vacuum, which we think of as emptiness, have energy at all? But quantum mechanics reshapes this notion entirely. The vacuum isn't a barren void. It's a dynamic stage filled with invisible activity, a field full of possibilities. In fact, this quantum vacuum could hold the keys to understanding both the birth of the universe and its ultimate fate. To see how, let's begin with the nature of quantum fields. In quantum field theory, the framework that unites quantum mechanics and special relativity, everything in the universe is described not just as particles, but as excitations of underlying fields. Electrons, quarks, photons, all the particles we know, are ripples in these fields. Now, even if you strip away every particle, cooling a system to what seems like absolute emptiness, the fields remain. They cannot be turned off. And because of quantum uncertainty, these fields are never perfectly calm. They jitter, vibrate, and fluctuate at every point in space. This restless background is what we call the quantum vacuum. Vacuum energy, then, is the baseline energy of these fields when no real particles are present. You might imagine it as the quiet hum of an amplifier when no instrument is plugged in. Even when the stage is empty, there's a background buzz that can never be silenced. These fluctuations are subtle but real. we know they exist because they leave fingerprints in experiments. For instance, the Casimir effect demonstrates vacuum energy in action. When two uncharged metal plates are placed extremely close together in a vacuum, quantum fluctuations outside the plates exert pressure, pushing them together. This tiny but measurable force arises not from particles we can see, but from the energy of the quantum vacuum itself. Another striking example comes from atomic physics. The energy levels of electrons and atoms are shifted slightly by interactions with the fluctuating vacuum, a phenomenon known as the Lamb shift. These subtle changes, predicted by quantum electrodynamics and later confirmed experimentally, show that the vacuum is not an empty backdrop, but an active participant in physical processes. What we call nothing, in fact, contributes to the very structure of atoms and the behavior of matter. The implications of vacuum energy extend far beyond the laboratory. In cosmology, it plays a central role in some of the deepest mysteries of the universe. One of these mysteries is dark energy, the unknown force that appears to be driving the accelerated expansion of the universe. Observations of distant supernovae and the cosmic microwave background suggest that about 70% of the universe's energy content is this dark energy. One leading hypothesis is that dark energy may simply be the energy of the quantum vacuum, spread across the vastness of space. If so, the restless nothingness of quantum physics is not only real, but is shaping the destiny of the cosmos itself. However, this idea comes with a staggering puzzle. When physicists try to calculate the vacuum energy using quantum field theory, the numbers are absurdly large. So large, in fact, that if they were correct, the universe would have blown apart instantly after its birth. The actual observed value of dark energy is tiny by comparison, yet non-zero. Reconciling this discrepancy, known as the cosmological constant problem, is one of the great unsolved riddles in physics. It suggests that our understanding of vacuum energy is still incomplete, or that some deeper principle cancels out most of its effects, leaving only a faint residue. This tension reveals a profound truth. The vacuum is not nothing but a kind of cosmic engine whose inner workings we only partly understand. It may have been crucial in the very first moments of the Big Bang. Some theories propose that a burst of vacuum energy drove the universe into a phase of exponential growth known as cosmic inflation. In this scenario, the vacuum wasn't a passive stage. It was the fuel that powered the dramatic expansion that smoothed and structured the cosmos. Later, as inflation ended, the vacuum energy transformed into the matter and radiation that filled the universe. If this picture is correct, then the nothingness of the quantum vacuum is directly responsible for the existence of galaxies, stars, and us. But even deeper questions lurk here. If vacuum energy can fluctuate, could it not also fluctuate enough to spark an entire universe into being? Some physicists, like Edward Tryon in the 1970s, speculated that our universe might be the result of such a fluctuation. From this perspective, the universe didn't come from a true void. It came from a quantum vacuum, a fertile nothing that contained within it the possibility of everything. This doesn't eliminate the mystery. It only shifts it. We still must ask why there is a quantum vacuum at all, but it softens the paradox of creation by showing how nothing is not the sterile emptiness we imagine, but an arena bubbling with potential. The very phrase vacuum energy is a reminder that our intuitions about emptiness are outdated. In physics, the void is not a blank canvas. It's the paint, the brush, and perhaps even the artist all in one. Every cubic centimeter of empty space contains within it a roiling sea of fluctuations, fields, and possibilities. On human scales, these effects are subtle, almost invisible. But on cosmic scales, they may determine the birth, evolution, and fate of the universe. So when we talk about the vacuum, we should not think of nothingness at all. We should think of it as a field of hidden structure, a restless background that ensures even the quietest corners of the cosmos are alive with possibility. In the quantum universe, nothing is never truly nothing. It is the seedbed of creation itself. If vacuum energy shows us that emptiness hums with unseen activity, then the idea of virtual particles takes this strangeness one step further. These elusive entities embody the radical quantum truth that even when we strip the universe down to what we believe is nothing, there are still flickers of being that refuse to stay gone. Virtual particles are not science fiction. They are mathematical consequences of quantum theory, and they challenge our most basic notion of emptiness by revealing that the void itself behaves like a restless ocean of fleeting appearances and disappearances. To understand them, we need to return to the uncertainty principle. At the quantum level, the precision of a system's energy and the duration for which that energy exists are inversely related. This means that for very short timescales, energy can borrow itself into existence, provided it vanishes quickly enough to satisfy quantum rules. From this loophole emerges the concept of virtual particles. For an unimaginably brief moment, a particle-antiparticle pair can appear out of the vacuum, interact with real particles or fields, and then annihilate back into nothingness, leaving behind only subtle traces of their ghostly visit. The term virtual does not mean imaginary in the sense of being unreal. Instead, it means that these particles cannot be directly observed in the way we see electrons or protons. They exist within the quantum fields as intermediate states, allowed by the rules of quantum mechanics, but forbidden from persisting long enough to become permanent features of reality. Nevertheless, they are far from irrelevant. Their indirect effects can be measured, and those effects reshape the world around us. One of the clearest demonstrations of their influence is the Casimir effect, where two uncharged metal plates placed extremely close together in a vacuum experience a force drawing them together. What causes this? Virtual particles. The plates restrict the types of quantum fluctuations that can exist between them compared to outside, creating an imbalance in pressure. This pressure difference pushes the plates together. This experiment, carried out and confirmed, proves that the vacuum is not a tranquil void, but an active arena where virtual particles exert real forces. Another example comes from the behavior of black holes. Stephen Hawking famously showed that black holes aren't entirely black. They emit what we now call Hawking radiation. The mechanism relies on virtual particles. Near the event horizon of a black hole, a particle-antiparticle pair can emerge from the vacuum. Normally, they would annihilate each other almost instantly. But if one falls into the black hole while the other escapes, the black hole loses a tiny amount of mass as the escaping particle becomes real. Over vast spans of time, this process causes black holes to evaporate. That such a profound cosmological prediction rests on the behavior of virtual particles underscores their significance in the deepest workings of the universe. Virtual particles also play a central role in the interactions of fundamental forces. In quantum electrodynamics, for instance, the force between charged particles like electrons is mediated by the exchange of virtual photons. Similarly, the strong and weak nuclear forces are explained by the exchange of virtual gluons, W bosons and Z bosons. Without these unseen intermediaries, the structure of matter would collapse. The very atoms we are made of rely on virtual particles to hold them together. Thus, while they may be invisible to our instruments, their fingerprints are everywhere in the fabric of existence. What makes this all the more mind-bending is that virtual particles exist everywhere and at all times. Even in the deepest vacuum of intergalactic space, where there is no detectable matter or radiation, the vacuum is alive with particles continually flickering in and out of existence. They are not an anomaly. They are the default behavior of nothingness itself. Emptiness, in the quantum view, is more like a boiling pot of water than a still pond. The particles appear, vanish, and reappear with such frenetic inevitability that we must abandon entirely the classical picture of void as a place of stillness. This realization reshapes the way we think about the Big Bang. If the vacuum is inherently unstable, if particles can pop into being even fleetingly, then perhaps the leap from nothing to something is not such a leap at all. It may be a natural outcome of the quantum rules governing existence. The same principles that allow virtual particles to flicker into being for fractions of a second may, on an unimaginably grander scale, allow an entire universe to erupt from quantum fluctuations. What seems miraculous at the human scale might be woven into the fabric of reality itself. Still, the existence of virtual particles raises profound questions. If they appear everywhere, does that mean there is no such thing as absolute emptiness? Can we even speak meaningfully about nothing when the laws of physics demand that something, however fleeting, must always be happening? For many physicists, the answer is no. The void is not the end of existence, but another mode of existence, an active state, full of ephemeral appearances, structured by the very laws of quantum mechanics. So when we picture nothing, we should not imagine a dark, silent void. Instead, we should imagine a stormy quantum sea, with virtual particles endlessly bubbling into and out of reality, shaping forces, altering energy levels, and perhaps even opening the door for universes themselves to arise. The vacuum is not a barren absence. It is the most fertile nothing imaginable, a cauldron of possibility that refuses to ever sit still. Having seen how virtual particles flicker in and out of existence, reshaping our notion of nothing, we're now ready to consider how such restless quantum activity may have ignited one of the most important events in cosmology: cosmic inflation. This theory suggests that our universe, with its galaxies, stars, and vast stretches of spacetime, may have been born not from a steady unfolding, but from an unimaginably brief and violent burst of expansion. Inflation provides a bridge between the quantum foam of nothingness and the large-scale universe we see today, showing how a tiny fluctuation could blossom into the cosmos itself. To grasp inflation, we need to step back and look at a puzzle the Big Bang model alone couldn't solve. The standard Big Bang theory describes the expansion of the universe well, but it leaves some questions hanging. Why does the universe look so uniform on large scales? The cosmic microwave background radiation, the afterglow of the early universe, is nearly the same temperature in all directions, even though regions of space so far apart should never have been in causal contact, meaning they couldn't have exchanged information or energy to even out. This is called the horizon problem. Another puzzle is the flatness problem. The universe appears to be geometrically flat, balanced on a knife's edge between collapsing back on itself and expanding too quickly for galaxies to form. And finally, the Big Bang alone doesn't explain why we don't see relics of exotic physics, like magnetic monopoles, that many early models predicted should exist in abundance. Cosmic inflation, first proposed in the early 1980s by physicist Alan Guth and developed by others like Andre Linde, came as a revolutionary solution. According to this idea, a fraction of a second after the Big Bang, the universe underwent exponential expansion, stretching faster than the speed of light for an incredibly brief period. This doesn't violate relativity, since space itself can expand without objects moving through it faster than light. In just 10 to the minus 36 to 10 to the minus 32 seconds, the universe ballooned from subatomic size to something unimaginably vast, ironing out wrinkles and irregularities. The horizon problem disappears because regions of the universe that look too far apart to have interacted were once close together before inflation stretched them apart. The flatness problem resolves because exponential expansion drives the geometry of space toward flatness, like zooming in on a balloon so much that its curve looks flat. And relics, like monopoles? Inflation dilutes them to such rarity that they effectively vanish. But where does this inflation come from? This is where the quantum vacuum and fluctuations re-enter the story. In inflationary theory, a special kind of field called the inflaton field filled the early universe. Its potential energy acted like vacuum energy on steroids, driving expansion at an exponential rate. Eventually, this field decayed, releasing energy that reheated the universe and created the particles, radiation, and structures we see today. And crucially, the tiny quantum fluctuations in this field, random jitters at the smallest scales, were stretched by inflation to cosmic scales. These fluctuations became the seeds of galaxies and cosmic structures. Without them, the universe would be smooth and lifeless. With them, matter clumped under gravity to form stars, planets, and ultimately, us. This connection between the quantum and the cosmic is breathtaking. It suggests that the vastness of the Milky Way, the glitter of starlight, and the swirl of galaxies all trace their roots back to tiny quantum jitters magnified by inflation. The randomness of quantum physics gave birth to the grand order of cosmic architecture. What could seem more paradoxical? That uncertainty itself became the blueprint for structure. Evidence for inflation is strong, though not yet definitive. The most compelling support comes from the cosmic microwave background, CMB. When satellites like COBE, WMAP, and Planck mapped the faint afterglow of the early universe, they found tiny temperature fluctuations that matched predictions of inflationary theory. The size and distribution of these fluctuations are consistent with quantum seeds stretched by inflation. In other words, The CMB carries an imprint of inflation written across the sky, like a fossil of the universe's birth. Still, inflation is not without its mysteries. We don't yet know what the inflaton field is, or whether it truly existed. Some physicists argue inflation is too flexible, able to accommodate almost any observation, and therefore hard to falsify. Others suggest alternative models, like bouncing cosmologies or string-inspired scenarios, that attempt to explain the same puzzles without inflation. Yet, despite debate, inflation remains the most elegant and widely studied explanation for the early universe's rapid growth. Perhaps the most provocative implication of inflation is that it may not have been a one-time event. Some versions of the theory suggest that inflation is eternal. While inflation ended in our region of space, it may continue elsewhere, constantly birthing new bubble universes within a larger multiverse. If so, our cosmos is just one patch of a much larger quilt, each patch with its own physical laws and histories. In this grander picture, the Big Bang wasn't the singular beginning of everything, but a local event within an infinite and endlessly creative backdrop. So inflation does more than solve technical problems. It reshapes how we imagine creation itself. A quantum fluctuation, once thought too small to matter, could have unleashed the chain reaction that expanded into the cosmos we inhabit. The void, restless with energy, gave rise to fields. The fields gave rise to space-time, and the jitter of uncertainty became the foundation of galaxies. Inflation is the story of how nothing that was truly nothing could set into motion everything. If cosmic inflation showed us how a tiny quantum fluctuation could give birth to our universe, the multiverse hypothesis dares to take the next leap. What if our universe is not the only one? What if the Big Bang was not a singular, unique event, but merely one bubble in an endless froth of universes, each with its own laws, its own histories, its own possibilities? This idea expands the stage of existence from a single cosmic drama to an infinite theater where countless plays unfold side by side, unseen but potentially real. The multiverse hypothesis is one of the boldest and most controversial proposals in modern science because it challenges the comforting idea that our universe is all there is. The connection to inflation is crucial here. As we saw, inflation is thought to have ended in our region of space, releasing energy to form matter and radiation, but in many models, inflation never ends everywhere. Instead, while it stops in localized regions, creating bubble universes like ours, it continues indefinitely in others. This process is called eternal inflation. The result is a cosmic landscape where inflation is still raging in some regions, while in others, it has cooled to form discrete universes, each one a bubble expanding into the inflationary sea. Our universe is one such bubble, and beyond our cosmic horizon may lie countless others. Each bubble universe could, in principle, have its own laws of physics. That's because the properties of a universe, like the strength of forces, the masses of particles, or even the number of dimensions, may depend on how inflation ended in that region. Or on deeper physics, such as string theory's landscape, string theory predicts a vast number of possible vacuum states, each corresponding to a different way the extra dimensions of space could be compactified. If eternal inflation populates this landscape, then every possible version of physics is realized somewhere in the multiverse. Our universe, with its finely tuned constants that allow stars, chemistry, and life, might simply be one of many configurations. This perspective offers a provocative explanation for one of the greatest puzzles in cosmology, the apparent fine-tuning of the universe. Why are the laws of physics so precisely set that life can exist at all? For example, if the strength of the strong nuclear force were slightly different, atoms might never form. If the cosmological constant were larger, the universe would fly apart too quickly for galaxies to form. It seems as though the universe is delicately balanced to permit life. But in a multiverse, this fine-tuning is no miracle. It is selection. Out of countless universes with different properties, only those with the right conditions could ever host observers like us. We find ourselves in a universe suited for life not because it was designed, but because only such universes are observed. This is sometimes called the anthropic principle, and while it is philosophically unsettling, it is a natural consequence of the multiverse view. Of course, the multiverse is not without controversy. Critics argue that it may never be testable. By definition, other universes are causally disconnected from ours, separated by expanses of inflationary space we cannot cross. If we cannot observe them, can we call them science? Others reply that indirect evidence is possible. For example, if two bubble universes ever collided in the early cosmos, they might leave scars, subtle imprints in the cosmic microwave background. Some cosmologists have searched for such patterns, though so far no conclusive evidence has emerged. Additionally, the mathematical frameworks of inflation and string theory strongly suggest that the multiverse is a natural outcome. Even if we cannot see it, it may be the logical extension of theories that already explain our universe well. Beyond inflation, other versions of the multiverse arise from different corners of physics. The quantum many-worlds interpretation suggests that every quantum event spawns parallel realities, each equally real but inaccessible to each other. There are also ideas of brain-world multiverses from string theory, where our universe is a three-dimensional surface floating in a higher-dimensional space alongside others. These versions differ in mechanism, but they all expand the idea that our universe may be one of many. The multiverse also forces us to rethink our place in existence. If there are infinite universes, then everything possible may happen somewhere. There may be universes where stars never formed, universes where life evolved differently, universes where the laws of mathematics themselves take unfamiliar forms. In such a vast ensemble, our universe may not be central, nor unique. It is simply one bubble in an infinite sea. For some, this is liberating. It removes the burden of cosmic uniqueness. For others, it is unsettling. It strips our universe of specialness and replaces it with statistical inevitability. But perhaps the most profound aspect of the multiverse hypothesis is how it reframes the question of nothing. If our universe is one bubble among many, then it did not emerge from true nothingness but from a larger something, the inflationary background, the string landscape, or the timeless laws that govern them. In this view, the Big Bang was not the creation of all existence, but a local unfolding within a grander reality. Nothing, it seems, keeps retreating as science advances. What we once thought was void turns out to be fertile. What we once thought was unique turns out to be plural. So the multiverse is not merely a wild speculation, it is a natural consequence of some of the best ideas in physics. While evidence remains elusive, its conceptual power is undeniable. It takes the restless nothing of quantum physics and expands it into an endless something, where universes bubble and bloom without end. If true, the multiverse means that our universe is not the story, but one story among an infinite library of possible tales. The idea of the multiverse opens our imagination to a reality where countless universes may exist side by side, each with its own fate. But what if our own universe, instead of being a solitary bubble or one among many, is itself part of a repeating cycle, an eternal rhythm of birth, death, and rebirth? This is the premise behind cyclic universe models, which suggest that the cosmos may not have a single moment of creation at all, but instead oscillates through endless stages of expansion and contraction. In such a picture, the Big Bang was not the absolute beginning, but merely the latest in a series of cosmic beats in an infinite symphony. The idea of a cyclic universe is not new. Ancient mythologies and philosophies often imagine time as circular, rather than linear, with creation and destruction recurring endlessly. Modern science, surprisingly, has begun to revisit this ancient intuition, though framed in mathematical and physical terms. One of the earliest scientific versions of the cyclic universe arose as a response to the Big Bang's troubling singularity. If the universe expands from an infinitely dense point, the equations break down. But what if instead the expansion is temporary, destined to reverse under gravity? In the 20th century, some cosmologists proposed a model where the universe expands for billions of years, slows down, and then contracts in a big crunch. When all matter collapses back into an ultra-dense state, the process triggers a new Big Bang, beginning another cycle. Expansion, contraction, rebirth, an infinite loop with no first cause. For a while, this idea was appealing. It eliminated the need for a singular origin and promised an eternal cosmos. But as observations grew more precise, evidence showed that the universe's expansion is accelerating, driven by dark energy. If this acceleration continues indefinitely, the universe will not collapse into a big crunch. It will instead expand forever, growing colder and emptier with time. This seemed to put an end to simple oscillating models. Yet, cyclic ideas have not disappeared. Instead, they have evolved. A modern variant comes from string theory and higher dimensional physics, often referred to as the ekpyrotic or cyclic model. In this scenario, our universe is a three-dimensional brane, a kind of membrane, floating in higher dimensional space. Occasionally, our brane collides with another parallel brane. The collision releases enormous amounts of energy, manifesting as a Big Bang. After expanding, the universe may eventually stabilize until another collision occurs, triggering a new cycle. Here, the cycle is not one of contraction and collapse, but of collisions in a higher dimensional arena. Another cyclic model modifies the mathematics of general relativity itself. Loop quantum cosmology, an offshoot of loop quantum gravity, suggests that the Big Bang singularity is replaced by a big bounce. According to this framework, as the universe contracts, quantum effects prevent densities from reaching infinity. Instead, space-time becomes repulsive at extremely small scales, causing the universe to rebound and expand again. The cosmos thus oscillates between big bangs and big crunches, but never collapses into a true singularity. What makes these cyclic scenarios so intriguing is how they reframe the question of before. In a cyclic universe, asking what was before the Big Bang becomes meaningless in a different way than in relativity's singularity. It isn't that time ceases to exist, but that time extends indefinitely backward, with cycles stretching into the infinite past. Each cycle may differ slightly from the last, but the process itself has no beginning. The cosmos has always been. Of course, cyclic models face challenges. One issue is entropy. According to the second law of thermodynamics, entropy, disorder, tends to increase over time. In a truly cyclic universe, this would mean each cycle should be more disordered than the last. Eventually, the cycles would unravel into chaos. Some models address this by proposing mechanisms that reset entropy, perhaps through the enormous expansion of space-diluting disorder, before each new cycle begins. Others suggest entropy is stored in extra dimensions or shed into horizons we cannot observe. Despite these difficulties, cyclic models carry a powerful philosophical allure. They remove the need for a singular creation event and replace it with eternal recurrence. The universe requires no first cause because it never truly began. Every bang is preceded by a crunch, every expansion by a contraction. From one perspective, this is comforting. It avoids the puzzle of something emerging from nothing. From another, it's dizzying. The idea of infinite cycles stretches imagination beyond comprehension. And yet, cyclic cosmologies fit naturally with humanity's long-standing sense of rhythms in nature. Day follows night, seasons follow seasons, stars are born and die in cycles. Perhaps the universe itself follows a grander version of these patterns, endlessly renewing itself. Whether through brane collisions, quantum bounces, or other mechanisms yet to be discovered, the cyclic universe invites us to see the Big Bang, not as a once-in-history miracle, but as part of an eternal heartbeat of existence. When scientists considered the cyclic universe, they were drawn to the elegance of an eternal cosmic rhythm. Yet, some thinkers went even further and asked, what if the universe is finite but without any true beginning at all? Among the boldest answers came from Stephen Hawking and James Hartle in the 1980s, who developed what is now known as the no-boundary proposal. This idea sought to resolve the paradox of creation without resorting to infinities or external causes. Hawking's vision was that the universe could be finite, like the surface of a sphere, but without a sharp edge or starting point, an origin that is smooth, self-contained, and boundaryless. To appreciate this, think of the Earth. Our planet has a finite surface area, yet, if you travel in any direction, you will never find a boundary. You may reach the North Pole or the South Pole, but you will not encounter a cliff where the planet simply ends. The surface is finite but unbounded. Hawking and Hartle applied this analogy to time itself. They suggested that near what we think of as the beginning of the universe, time does not behave like time as we normally experience it. Instead, it behaves like another spatial dimension. In this imaginary time, the universe can be finite yet have no distinct beginning. Just as there is no edge to the Earth, there would be no edge to time. The no-boundary proposal relies on the strange mathematics of quantum cosmology. Hawking and Hartle proposed that the universe's wave function the quantum description of all possible states, does not require a singular boundary condition. Instead, the universe can be described as emerging smoothly from a timeless quantum state. In this picture, the Big Bang was not a sharp point of creation, but more like the south pole of a sphere, a smooth, rounded cap where ordinary time transitions into imaginary time. Asking what came before this is like asking what is south of the South Pole. The question dissolves, because the concept of before doesn't apply. This proposal was radical because it challenged the very language of beginnings. In traditional Big Bang cosmology, time has a starting point, and that naturally invites the question of what came before. In cyclic cosmologies, time stretches infinitely backward in repeated loops. But in the no-boundary view, time as we know it is simply not the right framework to apply to the earliest phase of the universe. There was no before, not because time began suddenly, but because the geometry of the universe makes before irrelevant. The elegance of this idea is that it avoids singularities. In general relativity, the singularity at the Big Bang is a place where physics collapses into infinities. But in the no-boundary proposal, the universe emerges smoothly from a quantum state, like a ball rolling gently out of a curved landscape rather than exploding out of a pinprick. There is no mathematical breakdown, just a transition from a timeless quantum regime to the expanding cosmos we observe today. Philosophically, the no-boundary proposal is as unsettling as it is beautiful. It eliminates the need for a cosmic first cause. If the universe is self-contained and finite with no boundary conditions, then there is no place to insert a creator, a trigger, or an outside. The universe simply is. Hawking himself emphasized this point. If the universe has no boundary, then the question of who set it going becomes irrelevant. There is no before that requires explanation. The cosmos exists as a self-contained entity, governed by physical laws that are complete in themselves. Of course, the no-boundary proposal is not without its critics. Some argue that the mathematics is elegant but speculative, lacking definitive observational evidence. Others suggest alternative quantum cosmology models that also avoid singularities but differ in detail. Yet, even with uncertainties, the no-boundary idea has profoundly shaped cosmological thinking. It provides a conceptual framework for imagining a universe that is finite in scope but infinite in self-sufficiency, a cosmos without an edge either in space or in time. In many ways, the proposal pushes us to expand our imagination beyond linear notions of beginnings and endings. It suggests that the deepest mysteries of existence may not be answered by asking what happened first, but by rethinking whether first even makes sense. Instead of picturing the universe as a story with a first chapter, Hawking and Hartle invite us to think of it as a globe, finite, whole, and without a sharp start. This vision does not settle the mystery of why there is something rather than nothing, but it reframes the puzzle. If the universe has no boundary, then perhaps it requires no external explanation. It exists because existence is what the laws of quantum physics permit. For some, this is liberating, a vision of a self-sustaining cosmos. For others, it is unsettling, as it leaves no room for the familiar comfort of causes, beginnings, or external origins. Still, the no-boundary proposal remains one of the most imaginative and profound attempts to confront the problem of cosmic beginnings. It challenges us to accept that nothing and before may not be meaningful concepts at the ultimate level. Instead, the universe may be a seamless whole, finite yet unbounded, a cosmic sphere of existence that needs no beginning because it already is complete. The no-boundary proposal invites us to abandon the idea of a clear cosmic starting line, suggesting that the universe might be self-contained and need no external trigger. Yet even with such elegant models, we cannot avoid the deepest and oldest paradox of all. Can something come from nothing? This is the core of the logic of beginnings, a question that has haunted philosophy, theology, and science alike for millennia. It is not just a scientific puzzle, but a challenge to reason itself, because the very act of asking forces us to confront the foundations of causality, existence, and the meaning of nothing. At its simplest, the paradox runs like this. If the universe exists, did it have a cause? If so, what caused that cause? If we follow this chain back far enough, do we end up at a first cause? Something uncaused, timeless, and necessary? Or is it possible that the universe itself simply exists without cause, not as a result of anything, but as a brute fact? Both answers feel troubling. A first cause raises the question of why it exists rather than nothing. A self-existing universe defies our intuition that everything must come from something. We are caught in a logical tug-of-war where either side challenges our deepest assumptions. This paradox was well known to philosophers long before modern cosmology. Aristotle argued for an unmoved mover, a necessary, eternal entity that set everything in motion without itself being caused. Medieval thinkers like Thomas Aquinas expanded this into arguments for God as the first cause of existence. The logic seemed compelling. Everything we see is contingent, dependent on something else, so there must be a necessary being at the foundation. Without it, how could there be anything at all? Yet, modern science complicates this reasoning. If time itself began at the Big Bang, then perhaps there was no before in which a cause could operate. In that case, asking for a first cause may be like asking for the north of the North Pole. It simply doesn't apply. On the other hand, quantum physics shows us that causality itself may not be as strict as we imagine. In the quantum world, particles can appear without a clear cause, emerging briefly from the vacuum as virtual particles before disappearing again. Radioactive decay occurs spontaneously without any specific trigger. If the smallest building blocks of nature behave this way, perhaps the universe itself could have originated in a similar fashion, uncaused, a quantum fluctuation on a cosmic scale. In this light, the question, can something come from nothing, becomes less shocking. Perhaps nothing is unstable, destined to give rise to something. Still, not everyone is satisfied with this explanation. Critics argue that saying the universe arose from a quantum fluctuation merely shifts the mystery. After all, where did the quantum fields and laws of physics that allow such fluctuations come from? They must exist in some sense for the fluctuation to occur. If so, then we haven't really explained creation from nothing. We've explained creation from a hidden something. The problem of beginnings refuses to go away. Some thinkers embrace the idea that the universe could be a brute fact without cause or explanation. In this view, existence is not something that requires justification. The universe, or multiverse, just is. This is uncomfortable because our minds are conditioned to look for reasons, to demand causes, but perhaps the demand for explanation does not apply at the ultimate level. Maybe reality is self-sufficient, needing no reason beyond itself. As the philosopher Bertrand Russell once put it, the universe is just there, and that's all. Others argue that the universe's existence may be tied to principles of symmetry or balance. For instance, if the total energy of the universe is zero, because the positive energy of matter is balanced by the negative energy of gravity, then perhaps the universe can exist without violating any rules of conservation. In this sense, the universe does not come from nothing, but from a state of perfect balance, where something and nothing blur into each other. The laws of physics may permit, or even require, such a state to blossom into a cosmos. The logic of beginnings, then, forces us to wrestle with the possibility that our intuitions may not apply at all scales. In our everyday world, causes precede effects, and nothing comes from nothing. But at the cosmic level, time may not have a before, causality may not be absolute, and existence may not need a reason. What feels like paradox to us may simply be the way reality operates, indifferent to human logic. And yet, the very fact that we ask this question shows something profound about human beings. We cannot help but wonder why there is something rather than nothing, why the universe exists at all. Whether the answer is a first cause, a timeless cycle, a quantum fluctuation, or a brute fact, the logic of beginnings pushes us to the limits of reason, where science, philosophy, and wonder converge. Perhaps the ultimate resolution is not to find a final answer, but to accept that the question itself is part of the mystery, an invitation to reflect on the strangeness of existence, and to marvel at the fact that there is a universe here to ponder it. The logic of beginnings presses us to confront whether something can truly emerge from nothing, or whether the universe simply is, without cause or justification. That paradox alone challenges our deepest assumptions about reality. But modern physics takes the discussion one step further by proposing that perhaps the universe did not come from nothing in the absolute sense at all, but from a state of perfect symmetry and balance. In such a state, the sum of everything could add up to nothing, and yet within that nothingness, the seeds of existence were already encoded. This is where the idea of symmetry and quantum origins enters the stage, a vision of creation in which the universe arises not from a void, but from equilibrium, a delicate balance where opposites cancel yet still allow for emergence. To understand this, we need to appreciate how profoundly symmetry governs the physical world. In physics, symmetry is not merely aesthetic, but fundamental. It means invariance, when something remains unchanged under a transformation. For example, rotate a perfect circle, and it looks the same. In physics, similar principles apply. The conservation laws that structure our universe are tied directly to symmetries. Conservation of energy corresponds to symmetry in time. Conservation of momentum corresponds to symmetry in space. Conservation of electric charge arises from gauge symmetry. This profound link, articulated through Emmy Noether's theorem, shows that the universe's deepest laws are written in the language of balance and symmetry. Now consider the possibility that the early universe, or the state before the universe, was one of perfect symmetry. In such a state, all forces, energies, and fields could be unified. There would be no distinction between matter and antimatter, positive and negative, space and time, or even the familiar forces of gravity, electromagnetism, and the nuclear interactions. Everything would be one seamless whole. In this state of perfect balance, the net energy could even be zero. The positive energy of matter and radiation might be exactly cancelled by the negative energy of gravity. In other words, the total cost of creating the universe could be nothing. As cosmologist Alan Guth once remarked, the universe is the ultimate free lunch. This is not mere poetic speculation. It's grounded in serious physics. In general relativity, gravity carries negative energy. When you form a planet, the positive energy of its mass is offset by the negative gravitational binding energy. Extend this to the cosmos. If the total positive energy of matter and radiation is perfectly balanced by the negative energy of gravity, then the universe's total energy could be exactly zero. From this perspective, creating a universe doesn't require inserting something from outside. It only requires a fluctuation in which balanced energies emerge. The net result is nothing, but that nothing is structured in such a way that everything exists within it. Quantum mechanics deepens this picture. In quantum theory, systems do not remain locked in perfect balance forever. They fluctuate, they tunnel, they explore possibilities. Imagine a pencil balanced perfectly on its tip, a state of perfect symmetry. In principle, it could stay that way forever. In practice, the tiniest disturbance will tip it over, breaking the symmetry and selecting a direction. In physics, this process is known as spontaneous symmetry breaking. The early universe may have been like that pencil, perfectly symmetric, timeless, balanced. But quantum fluctuations could have tipped it, breaking the symmetry and giving rise to the differentiated universe we see today, with distinct forces, particles, and directions of time. One compelling idea is that the arrow of time itself, the flow from past to future, arose from such a breaking of symmetry. In a perfectly symmetric state, there would be no distinction between forward and backward. But once symmetry broke, entropy began to increase, and time as we experience it was born. In this sense, the very flow of time could be an emergent property of a universe that started from balance and imperfection. Symmetry-based ideas also appear in particle physics. The Standard Model suggests that in the earliest fractions of a second after the Big Bang, all fundamental forces may have been unified. As the universe cooled, symmetries broke, and the forces separated into the four we know today: gravity, electromagnetism, and the strong and weak nuclear forces. This process resembles the way water, as it cools, crystallizes into ice. The underlying symmetry of liquid water gives way to the structured lattice of solid ice. In cosmology, the breaking of primordial symmetries didn't just diversify forces, it also seeded the matter-antimatter imbalance that allowed matter to dominate and galaxies to form. Without symmetry breaking, there would be no stars, no planets, and no us. What's extraordinary here is that nothing, when defined as perfect balance, is not sterile at all. It is a poised condition, like a violin string tuned to perfect silence but ready to vibrate at the slightest touch. In such a state, the universe could be self-contained, requiring no external agent to spark it. The laws of quantum physics, with their inherent fluctuations, may have provided the nudge that tipped the balance, unleashing the cascade of creation. Of course, this view raises further questions. If the universe came from a state of perfect symmetry, what established that symmetry in the first place? Are the laws of physics themselves eternal, existing independently of the universe they describe? Or do they, too, emerge from some deeper, more abstract level of reality? Physicists like Lawrence Krauss have argued that the laws of physics allow a universe to come from nothing, but critics point out that his nothing is really a structured something, a quantum vacuum governed by laws. Once again, the word nothing slips through our fingers. Nevertheless, the symmetry approach provides a striking resolution to the paradox of beginnings. Instead of something emerging from a true void, the universe emerges from balance, where positive and negative cancel. Existence becomes possible not in spite of nothingness, but because of it. The universe is not something from nothing, but something from zero, the neutral, poised state that holds both opposites within it. This vision transforms the way we think of nothing. It is not emptiness, but a canvas of perfect balance. It is not a void, but a hidden fullness where every possibility exists in superposition. When symmetry breaks, the fullness unfolds, and the cosmos emerges. Out of equilibrium comes diversity, out of balance comes creation, out of zero comes infinity. The idea that the universe could emerge from balance, where positives and negatives cancel to yield a net nothing, naturally leads us into a deeper reflection on the mathematics of nothingness itself. Mathematics has always been humanity's most precise language for describing reality, and when it comes to the concept of nothing, math offers tools that are both elegant and perplexing. By examining how zero, void, and nothingness are treated in mathematics, we begin to see why these abstract notions matter profoundly for physics, and why our very conception of nothing may be far richer than it first appears. Let us begin with zero. The number zero is one of the most powerful and revolutionary ideas in the history of human thought. Yet, it is also one of the strangest. Ancient civilizations could count, add, and subtract long before they had a formal concept of zero. The Babylonians, Egyptians, and Greeks had sophisticated mathematics, but they did not think of nothing as a number in its own right. The invention of zero as both a placeholder and a number, which emerged in ancient India and spread through Arabic mathematics into Europe, was a turning point. Suddenly, absence itself could be represented, calculated with, and built into the structure of equations. Zero became the foundation for positional notation, algebra, and eventually the entire edifice of modern mathematics. What is remarkable about zero is that it captures both emptiness and balance. It is the symbol for nothing, but it is also the fulcrum around which positives and negatives pivot. On a number line, zero is the center, the neutral point between opposites. Without zero, we cannot speak of symmetry, cancellation, or balance. In this sense, the mathematical treatment of nothing directly mirrors the physical idea of a universe emerging from balanced energies. Zero is not simply the absence of value. It is the reference point from which values make sense. Mathematics also provides other ways of formalizing void. In set theory, for example, we encounter the concept of the empty set, the set that contains nothing. This is not a number but a collection, defined precisely as the absence of elements. And yet, the empty set is not trivial. It is foundational. From the empty set, through successive operations, mathematicians can construct the natural numbers themselves. In other words, all of mathematics can be built upon the concept of nothingness, structured step by step into the fullness of number and logic. The void becomes the seed of everything. In physics, these mathematical ideas are not mere abstractions, they matter. When physicists describe the vacuum of space, they often use zero as a reference point. Zero energy, zero particles, zero temperature. But, as quantum mechanics shows us, the vacuum never truly equals zero. Fluctuations disturb the calm, virtual particles flicker in and out, and vacuum energy refuses to vanish. Here, the mathematical ideal of zero collides with physical reality. The vacuum strives for zero, but never attains it. The distinction between mathematical nothing and physical nothing becomes crucial. Mathematics allows perfect emptiness, but nature may forbid it. Zero also plays a critical role in equations that describe the universe's structure. Consider Einstein's field equations in general relativity. They balance the curvature of spacetime with the energy and momentum of matter. When the right-hand side of the equation is zero, meaning no matter or energy is present, the left-hand side still permits curved spacetime solutions, like gravitational waves. Even in the absence of matter, spacetime itself can ripple and evolve. Thus, the zero in Einstein's equations does not mean stillness or emptiness, but possibility. In cosmology, zero resurfaces in the form of total energy. As mentioned before, many physicists suggest that the total energy of the universe might be exactly zero, with positive and negative contributions canceling out. This is more than a numerical curiosity. It hints that the existence of the universe does not violate any fundamental principle. If the sum is zero, then the universe could, in principle, arise spontaneously without requiring an external source of energy. Here again, the mathematics of nothing becomes the physics of creation. But mathematics also warns us of the dangers of nothingness. Division by zero, for instance, produces undefined results, singularities. In physics, singularities appear in the equations of general relativity when densities or curvatures become infinite, such as at the center of black holes or at the Big Bang. These infinities are signals that our current theories have reached their limits, much as dividing by zero signals the collapse of arithmetic rules. Thus, while zero allows balance and structure, it also marks the boundary where known laws break down. It is both the anchor of mathematics and the crack through which mysteries slip. What is most profound here is how mathematics reveals nothingness not as an absence, but as a structure. Zero, the empty set, and null values are not voids in the sense of being meaningless. They are carefully defined concepts that provide the scaffolding of all logical systems. Without them, mathematics collapses. And because physics relies on mathematics to describe reality, the way we treat nothingness mathematically shapes how we conceive of it physically. So when we ask whether the universe could come from nothing, mathematics offers a subtle answer. If nothing is zero, then perhaps yes, because zero already encodes balance, symmetry, and the potential for opposites. If nothing is the empty set, then perhaps yes, because from that structured void, all mathematics, and thus all physics, can be constructed. But if nothing is an absolute absence, beyond even mathematical definition, then the question slips beyond our tools, leaving us with silence. In this way, the mathematics of nothing does more than describe emptiness. It reveals how emptiness is never really empty. Zero is both void and balance, both absence and foundation. It is the quiet point from which all else emerges, just as the universe itself may have emerged from a poised state of balance. To contemplate nothing in mathematics is to realize that nothingness is structured, fertile, and indispensable. It is the shadow of something, and perhaps the womb of everything. The mathematics of nothing reveals how even emptiness has structure, how zero and the void can serve as foundations for logic and physics. But while mathematics offers us abstract clarity, our actual ability to observe the universe is bound by unavoidable limits. We may theorize about beginnings, symmetries, and quantum origins, but the act of observation itself confronts a horizon beyond which we cannot see. This boundary is not a product of flawed instruments or lack of technology. It is woven into the very fabric of the universe. And because of it, the question of what lies before the Big Bang, or even beyond our observable patch of cosmos, may forever remain hidden from direct view. To understand this, we need to think about the nature of light and distance. Light travels at a finite speed, about 300,000 kilometers per second. That speed, while incredibly fast, is not infinite. This means when we look at the sky, we are not seeing things as they are now, but as they were in the past. The moon appears as it was about 1.3 seconds ago, the sun as it was 8 minutes ago, and distant galaxies as they were millions or billions of years ago. In effect, telescopes are time machines, allowing us to look backward through cosmic history. But this time machine has a limit. The universe itself has a finite age, around 13.8 billion years. No matter how powerful our telescopes become, we cannot observe events that happened earlier than the emission of the first light. The earliest direct snapshot we possess is the cosmic microwave background, CMB, the faint afterglow of the hot early universe, released about 380,000 years after the Big Bang, when the first atoms formed and light could travel freely. Before that, the universe was opaque, a dense plasma where photons scattered constantly. The CMB is therefore our cosmic horizon, a wall of fog beyond which light cannot carry information to us. We can infer, calculate, and simulate the earlier universe, but we cannot see it directly. Even more striking is the concept of the cosmic horizon. Because the universe is expanding, there are regions of space so distant that their light will never reach us, no matter how long we wait. The expansion of space stretches the wavelengths of photons, redshifting them until they fade beyond detectability. Beyond about 46 billion light-years in any direction lies the edge of the observable universe. This does not mean the universe itself ends there. It may extend infinitely beyond, but it is the furthest we will ever be able to observe. The horizon is not a physical wall, but a limit imposed by the expansion of space and the finite speed of light. This limit has profound consequences. It means we can never know with certainty what the entire universe looks like. We may live in an infinite cosmos, or in one curved back upon itself, or in one bubble among many. But because we can see only a fraction, our cosmic picture will always be incomplete. It is as if we live in a vast forest, but can only see the trees within a narrow circle around us. We can guess at the shape of the forest, but we cannot confirm it. When it comes to the Big Bang, the observer limits are even stricter. The further back we try to look, the more opaque the universe becomes. Before the CMB, we are left only with indirect probes, the distribution of elements forged in the first minutes, the statistical patterns of fluctuations imprinted in the CMB, and the predictions of theories like inflation. These are powerful clues, but they are not direct vision. The singularity itself, if it even existed, is forever hidden from us. We can model what conditions must have been like, but we cannot see the moment of creation. Asking to observe before the Big Bang is therefore impossible in principle. It lies outside not just our instruments, but the causal structure of the universe. This limitation humbles us. It reminds us that no matter how advanced our science becomes, there will always be boundaries to our knowledge. Some cosmologists liken it to trying to see beyond the edge of a balloon while living on its surface. The surface itself may stretch indefinitely, but we cannot step off it to look at the whole. We are confined within the horizon of our own universe. Yet, these boundaries are not failures. They are part of the structure of reality, and they guide us toward creative thought. Because we cannot observe directly, we construct theories that reach beyond the horizon, like inflation, the multiverse, or the no-boundary proposal. These theories are constrained by what we can see, but they also venture into realms we cannot test directly. It is a balance between evidence and imagination, between humility and daring. The limits of observation also intersect with philosophy. If we can never see before, does it even make sense to ask what lies there? Some argue that science should confine itself to what can be measured. Others argue that the human mind is compelled to push beyond, to imagine, to seek meaning even in the unobservable. The cosmic horizon becomes not just a physical boundary, but a metaphor for the limits of reason itself. So when we consider the question of nothing before the Big Bang, we must acknowledge that our observations will never answer it fully. The horizon is fixed, the fog is impenetrable, and time itself may have begun with the universe. Yet, within those limits lies the beauty of the mystery. Science does not collapse under its boundaries. It flourishes against them, using every clue available to sketch a picture of what might lie beyond sight. The cosmic horizon reminds us that some answers will always remain hidden, but that the act of asking, imagining, and theorizing is part of what makes us human. The reality of observer limits leaves us with an inescapable truth. There are boundaries to what we can ever directly see or measure. The cosmic horizon prevents us from observing the universe in its totality, and the opacity of the early cosmos blocks our view of the first few 100,000 years after the Big Bang. Beyond those barriers, what we have is not data in the ordinary sense, but inference, extrapolation, and most importantly, speculation. And here lies a central tension in cosmology. To meaningfully address questions about before the Big Bang, we must lean on speculation. even while acknowledging that speculation, by its nature, may never be confirmed. Speculation in science often has a misunderstood reputation. In everyday language, to speculate can mean to guess wildly without evidence. But in the scientific context, speculation is not random or arbitrary. It is structured imagination, guided by mathematical consistency, empirical constraints, and logical coherence. It is what scientists do when they push beyond the limits of current data, building hypotheses and models that may or may not later find support. In cosmology, speculation is not a weakness, it is a necessity. Without it, we could never even attempt to approach the ultimate questions. Why is there something rather than nothing? Did time have a beginning? Is our universe unique or part of a larger ensemble? At the moment, science has no firm answers to what, if anything, preceded the Big Bang. Instead, there exists a landscape of hypotheses. Each is informed by physics, mathematics, and creativity, but each remains unproven. We have inflationary models that propose quantum fluctuations sparked the universe's rapid expansion. We have multiverse theories that imagine countless other universes arising in a larger space of possibilities. We have cyclic models, brain-world collisions, loop quantum cosmology, and Hawking's no-boundary proposal. These ideas differ wildly, but what unites them is that they are attempts to move beyond the singularity problem, to find a coherent way to talk about the apparent beginning without running into the infinities and paradoxes that plague our current theories. Take inflation, for example. It is not simply a wild guess. It was proposed to solve specific problems in the Big Bang model, and its predictions match observations of the cosmic microwave background. But the precise mechanism of inflation remains speculative. What field drove it? What triggered its end? Did it happen only once, or is it eternal? Each of these questions leads to multiple speculative answers, and so far, none are confirmed. The success of inflation in explaining some puzzles does not automatically make it a complete account of before. It remains a powerful hypothesis awaiting deeper evidence. The multiverse hypothesis, too, is a form of speculation. It arises naturally from certain versions of inflation and from string theory, yet it faces the problem of testability. If other universes are causally disconnected from ours, how could we ever confirm their existence? Some cosmologists argue that indirect evidence, such as possible imprints of bubble collisions in the cosmic microwave background, might one day support the idea. Others argue that the multiverse is an unavoidable consequence of theories that already describe our universe well, and thus it should be accepted. But for now, the multiverse remains speculative. It is a conceptual leap into realms beyond observation. Cyclic cosmologies and the no-boundary proposal fall into a similar category. They offer elegant resolutions to the problem of beginnings, but they too rely on frameworks not yet confirmed experimentally. Loop quantum cosmology, for instance, predicts that the universe avoided a singularity via a bounce, but direct evidence of such a bounce may be forever inaccessible. Hawking's no-boundary proposal replaces the Big Bang singularity with a smooth, finite geometry, but this rests on mathematical extensions that may never yield testable consequences. These are not failures of science. They are examples of science pushing itself to its limits, stretching imagination to meet the unknown. Speculation is particularly necessary when grappling with the concept of nothing. Physics shows us that nothing may not exist in the way we imagine. The quantum vacuum seethes with fluctuations. Symmetry and balance can yield a net zero, yet still produce a structured reality. Mathematical nothingness is full of hidden frameworks, but whether this something disguised as nothing explains the ultimate origin remains unresolved. To bridge that gap, scientists speculate, sometimes controversially, about deeper laws or meta-laws, timeless frameworks that might govern even nothing. These are extraordinary ideas, but they are speculative because we cannot test them. It is important here to draw a distinction. Scientific speculation differs from pure metaphysics or philosophy because it remains tethered to possible evidence. A speculative hypothesis is judged by whether it is mathematically consistent, whether it connects to known physics, and whether it could, at least in principle, yield observable consequences. This tether keeps cosmological speculation scientific. Yet the further we reach into before the Big Bang, the more fragile the tether becomes, because the horizons of observation constrain us so tightly. This does not invalidate speculation, but it does mean that humility must accompany it. Some critics argue that too much speculation risks turning cosmology into mythology, stories told about unobservable realms. And indeed, the line between science and philosophy grows blurry at these extremes. But perhaps this is inevitable. The question of beginnings is as much philosophical as it is scientific. When we ask, why is there something rather than nothing, we are not merely asking for equations, we are asking for meaning. Science can provide models, probabilities, and structures, but the leap from how to why often lands in philosophy's territory. Speculation becomes the bridge, the way scientists engage with questions that stretch beyond empirical reach. That bridge is valuable even if the answers remain elusive. Speculative hypotheses guide research, inspire new experiments, and frame the way we interpret data. For example, speculation about inflation led to searches for specific patterns in the cosmic microwave background. Speculation about quantum gravity inspires physicists to study black holes, hoping their behavior will reveal hints of deeper laws. Even if we cannot directly observe before the Big Bang, speculation motivates us to probe the universe as far back as possible, to test every clue, and to refine our understanding of what nothing might mean. And speculation carries another role. It keeps human imagination alive. When Stephen Hawking asked what lies before time, or when Alan Guth imagined the universe as a free lunch, they were not simply calculating. They were expanding the boundaries of human thought. Speculation allows us to dwell in possibility, to sketch the outlines of realities we may never see, and to find meaning in the very act of wondering. So when we acknowledge that science has no firm answers about before the Big Bang, we are not admitting failure. We are recognizing the limits of evidence and the necessity of speculation. The hypotheses on the table are not final truths, but explorations, each offering a different vision of reality's ultimate nature. Whether the universe had a beginning or is eternal, whether it arose from symmetry or a multiverse, whether nothing even makes sense, all remain open. Speculation is not the end of science, but the frontier of it, the place where knowledge fades into mystery and imagination takes over. The role of speculation reminds us that science, when faced with the question of before the Big Bang, does not collapse into silence, but instead stretches imagination to its very limits. Yet one might still ask, why does this question matter at all? If we may never see beyond the cosmic horizon, if speculation cannot always be tested, why keep pressing against this mystery? The answer lies in the power of the question itself. Asking why the universe exists, or whether something can come from nothing, does more than fill scientific journals. It pushes the boundaries of physics, philosophy, and human imagination in ways that redefine how we see ourselves and our place in the cosmos. First, the question matters because it exposes the limits of our current theories. Physics thrives not only on its successes, but on the puzzles it cannot yet solve. The singularity at the Big Bang, the concept of before, the paradox of nothingness, these are not trivial gaps. They are profound cracks in the foundation. They remind us that general relativity and quantum mechanics, though powerful, are incomplete. By grappling with origins, scientists are driven toward the holy grail of modern physics, a unified theory that reconciles gravity with quantum laws. Without the challenge of beginnings, there would be less urgency to push for deeper frameworks like string theory or loop quantum gravity. Thus, the question of before is not idle. It is a compass pointing us toward the next frontier of knowledge. Second, this question reshapes our understanding of time and causality. In daily life, we take for granted that everything has a cause and that time flows steadily forward. But when cosmology confronts the possibility that time itself began at the Big Bang, it forces us to rethink these assumptions. If there was no before, then cause and effect reasoning may not apply to the universe's birth. This is not merely a technical point. It challenges the very way human beings think about existence. It asks us to imagine a reality where time is emergent, not fundamental, where the deepest truths may be timeless structures rather than sequences. By stretching our minds in this way, the question opens intellectual doors we never knew existed. Third, the mystery of beginnings matters because it touches on the problem of meaning. Humans are not content merely to catalog stars or measure forces. We want to know why there is a universe at all, why the laws of physics are the way they are, and whether existence itself has a reason. These are questions that straddle the line between science and philosophy. Even if physics someday develops a complete theory of quantum gravity, the deeper why may remain. Why these laws instead of others? Why any laws at all? In this sense, the question of nothingness matters because it reminds us that science is not only about equations, but also about wonder. Fourth, this question matters for the future of cosmology. Speculative models like inflation, the multiverse, or cyclic universes do more than describe possible beginnings. They suggest possible futures. If the universe is one bubble in a multiverse, then perhaps ours will eventually decay into another vacuum state. If the cosmos is cyclic, then everything we see may collapse and be reborn. If vacuum energy dominates forever, the universe may expand into eternal emptiness. In each case, the question of beginnings is tied to the question of endings. To ask what came before the Big Bang is also to ask what comes after us. It makes cosmology not just about the distant past, but about our ultimate fate. Fifth, the question matters because it is uniquely human. No other species we know of asks why the universe exists. Dogs and birds navigate space. Whales and dolphins communicate. Ants build societies. But only humans look at the stars and wonder about nothingness. To ask about before the Big Bang is to express something deeply human. The refusal to accept reality at face value, the drive to seek explanations even where none may be found. This capacity to question the foundations of existence is what fuels art, philosophy, and science alike. It is not just a scientific problem, it is a cultural and existential one. Moreover, the pursuit of this question shapes how humanity sees itself in the cosmic story. In ancient times, creation myths gave us frameworks of meaning. Today, cosmology offers new narratives, not myths in the traditional sense, but scientific models that still function as stories about origins. Whether it is a multiverse bubbling with countless universes or a cyclic cosmos reborn forever, these models give us new ways of imagining our place in existence. Even if speculative, they expand the horizon of human thought. To ignore the question would be to surrender one of the greatest opportunities for intellectual growth in history. Finally, the question matters because it reminds us of humility. The universe is vast, mysterious, and perhaps ultimately unknowable in its deepest origins. Yet, instead of despairing, humans persist in asking. This persistence itself is significant. It demonstrates that curiosity can flourish, even in the face of limits, that imagination thrives where certainty fails. Whether or not we ever fully answer what came before the Big Bang, the act of pursuing the question is a triumph of human spirit. It shows that science is not just about solving problems, but about embracing mysteries, about living in wonder at the boundary between knowledge and the unknown. In the end, asking why there is something rather than nothing matters because it stretches us. It stretches physics toward new theories, stretches philosophy toward new reflections, and stretches imagination toward new horizons. It forces us to live at the edge of what we can know and to accept that the edge itself is part of the beauty. Even if the question has no final answer, it matters profoundly because it defines what it means to be human, to look into the void, to ask, and to never stop seeking. All throughout this exploration, we've traced a path through some of the most profound mysteries humanity has ever faced. The Big Bang, the nature of time, the restless quantum vacuum, inflation, multiverses, cyclic models, and the limits of observation. Each perspective has given us glimpses into how science grapples with the question of beginnings and the possibility of nothing. Yet, after traveling through physics, mathematics, and philosophy, we arrive not at a final answer but at something far more humbling, and perhaps more beautiful. The recognition that nothing might not be nothing at all, and that the mystery itself is a gift. When people first hear the question, "What was there before the Big Bang?" they often imagine an absolute emptiness, a void like a blank canvas waiting for paint. But modern science has shown us that this mental picture may be fundamentally misleading. The deeper we look, the more we realize that the universe resists true emptiness. A vacuum is alive with fluctuations. Symmetry and balance allow opposites to cancel, yet still give rise to reality. Even zero and the empty set, mathematical symbols of nothingness, carry within them structure and potential. Nothing may not be sterile absence, it may be the most fertile state imaginable. And this realization reshapes the question itself. If the vacuum is never empty, if time may have begun with the universe, if space and laws are woven into existence itself, then perhaps asking what came before is like asking what lies beyond the edges of a sphere or past the final digit of infinity. It is not that the question is foolish, but that it forces us to confront the limits of human language and concepts. Nothing in physics is not the same as nothing in everyday speech, and before may not even apply at the deepest level of time. The mystery endures, but in enduring, it pushes us to expand our imagination. And there is wonder in that. There is wonder in the thought that galaxies and stars, life and consciousness, all trace back to fluctuations in a seething quantum vacuum. There is wonder in the possibility that our universe may be one bubble among countless others, each with its own laws, expanding endlessly in a vast multiverse. There is wonder in the idea that the cosmos may be cyclic, reborn again and again, pulsing with an eternal heartbeat. There is wonder, too, in Hawking's no-boundary vision, where the universe is finite but without edges, self-contained and complete. Every hypothesis, every speculation, paints a picture that is at once incomprehensible and profoundly beautiful. But perhaps the greatest wonder lies in the fact that we, fragile beings on a small planet orbiting an ordinary star, are capable of asking these questions at all. Against the backdrop of an infinite cosmos, we have developed minds that not only survive but ponder. We look into the night sky and do not stop at awe. We ask why. We take nothingness, a concept that seems meaningless to survival, and turn it into a frontier of thought. The ability to wrestle with these questions is itself evidence of something extraordinary. That consciousness is not just a byproduct of physics, but also a mirror in which the universe reflects upon itself. It is important to recognize that not having a final answer is not a defeat. The lack of closure is not a weakness, but a source of power. If science had resolved the question of nothing once and for all, the mystery would be gone, and so would the drive to explore. Instead, the unresolved nature of the question keeps curiosity alive, inspiring generations of thinkers to push deeper. Each hypothesis, whether inflation, multiverse, cyclic bounce, or no boundary, is not just a model of the cosmos, but a story we tell ourselves about possibility. These stories, even if provisional, enlarge the imagination and remind us that reality is richer than we can yet fathom. And maybe that is the point. Maybe the beauty of the mystery is not in solving it, but in living with it. The universe may never reveal what nothing truly means, but it has already revealed that nothing is not the void we once thought. Instead, it is layered, structured, vibrant with potential. To realize this is to realize that existence itself is a kind of miracle. Not in the supernatural sense, but in the sense that it is unexpected, unexplainable, and yet undeniable. The fact that there is something and not nothing is the greatest wonder of all. So, when we conclude this journey, let us not see the lack of answers as a dead end. Let us see it as an opening into infinite curiosity. The question, what was there before the Big Bang, may never be answered in a final, definitive way. But the act of asking it expands the boundaries of physics, stretches the capacity of human imagination, and deepens our sense of awe at the cosmos. The mystery is not a problem to be solved, but a beauty to be embraced. When you look up at the stars tonight, think of the paradox of nothingness. Think of the fact that emptiness is alive, that balance can give birth to universes, that time itself may be a child of the cosmos. Remember that what we call nothing may be the most extraordinary something of all. And let that realization fill you not with frustration at the unanswered, but with wonder at the infinite richness of the questions themselves. Because in the end, perhaps the truest answer to why nothing became something is this: that the universe is not only stranger than we imagine, it is stranger than we can imagine. And within that strangeness lies the beauty, the awe, and the joy of being part of the mystery. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.